Welcome to the Lion's Share podcast, where we break down today's most impactful research and bring fresh insights from the academic frontier straight to you.
Today, we're really aiming to trace the whole arc of AI from its earliest theoretical roots right up to today's corporate battles and this idea of an intelligence age. Because often you hear about AI innovation like it's purely a software thing, right? Better algorithms, bigger data. But the sources we've looked at, they argue pretty strongly that it's fundamentally about the hardware, the actual computer architecture, and crucially, the strategic moves companies made around that silicon.
That's exactly right. And for anyone listening, whether you're deep in academic research on innovation or setting strategy in the corporate world, the real question isn't if AI changes things, it's how you align your strategy with the nuts and bolts of computer architecture. You miss that hardware piece, you genuinely risk becoming irrelevant. So we need to unpack this whole story, starting way back, from von Neumann's models up to, well, the large language models we see everywhere now, but keeping a sharp eye on how hardware enabled and sometimes blocked progress.
Okay, let's do that. Starting point, mid-20th century. You got Alan Turing laying the groundwork, posing that fundamental question with the Turing Test, can a machine think? And then just a few years later, 1956, John McCarthy actually coins the term artificial intelligence at that famous Dartmouth Workshop. We saw early programs pop up pretty quickly after that. Things like the logic theorist, even Eliza, that early chatbot. Very symbolic, AI-focused.
But that early promise, it immediately slammed into a physical wall, a bottleneck. And this is where we have to talk about John von Neumann, an incredible polymath involved in everything from the bomb to game theory to, critically for us, computing. He established the dominant computer design for decades, what we now call the von Neumann Architecture. Basically, it's a design where the instructions for the program and the data it uses have to share the same pathway, the same memory bus.
Okay, so instructions and data competing for the same resources.
Exactly. And that creates what's known as the von Neumann bottleneck. Your processor might be fast, but it's constantly waiting for either the next instruction or the next piece of data to arrive from memory. It limits the actual computational speed.
Oh, I see.
And this absolutely hobbled early AI. Those symbolic AI systems trying to follow long chains of logic needed constant memory access. Later connectionist models, too. The ideas were there, sometimes quite complex, but the machines just couldn't physically feed the beast fast enough. That constraint was a major factor in the so-called AI winter.
Interesting. But was it only the hardware? I mean, weren't there questions about whether those symbolic, logic-based approaches were even the right way to model, messy human intelligence?
That's a really key point for strategic insight. It was likely both. There were conceptual hurdles. Sure, modeling the world purely with logic is tough. But the hardware limits were so severe, it was hard to even properly test the limits of the concepts. We couldn't know if better hardware might have saved some of those approaches because the hardware just wasn't there.
Okay, so the bottleneck was real. How did we start to break through it?
Well, the breakthrough wasn't initially AI-focused. It was fundamental physics and engineering. The transistor, invented back in 1947 at Bell Labs, that kicked off the whole semiconductor revolution.
Right, and this is where the familiar Silicon Valley story starts to unfold. You get the group leaving Shockley Semiconductor, founding Fairchild, and then key figures like Bob Noyce leaving Fairchild to start Intel. And Intel gives us the integrated circuit, then the first microprocessor, the 4004 in 71. This relentless shrinking, packing more and more transistors onto chips. Moore's law, that's what started chipping away at the von Neumann bottleneck, right? It provided the raw power needed for what came next.
Precisely. That scaling, that constant increase in computing power per dollar, eventually paved the way for the modern AI resurgence, which is really driven by deep learning. Deep learning, using these multi-layered neural networks, showed something incredibly important. It worked, and crucially, it scaled predictably. You threw more data and critically more compute at it, and the performance got better, often dramatically better. But it demanded computational power on a scale nobody had really dealt with before.
And the watershed moment for that was AlexNet in 2012, Hinton's work.
That's the one. Their win in the ImageNet competition wasn't just a win, it was proof. It showed that deep learning, powered by massively parallel processing on GPUs, could achieve results far beyond previous approaches. It basically announced, okay, the hardware is finally catching up to the ambition.
Which leads us straight to Nvidia.
Yes. This is where the hardware strategy becomes crystal clear. Nvidia started out making graphics cards for gamers, right? GPUs. But they realized these chips, designed for rendering a complex graphics which involves tons of parallel calculations, were almost perfectly suited for the math underlying deep learning neural networks.
So they pivoted.
They pivoted hard. They didn't just sell the GPUs. They built an entire ecosystem around them with their proprietary CUDA platform that stands for Compute Unified Device Architecture.
CUD, I've heard that term a lot. What exactly is it beyond just the hardware?
It's the software layer. It's a programming model, libraries, tools, everything researchers needed to actually program the GPUs for general purpose computing, specifically for the complex math of deep learning. Before CUDA, programming GPUs for non-graphics tasks was extremely difficult.
So it unlocked the potential of the hardware.
It unlocked it, and it created massive developer lock-in. Once researchers and companies started building their models using CUDA, training their people on CUDA, investing in Nvidia hardware, switching became really, really costly and difficult. It created incredibly powerful network effects.
And that explains their dominance. Over 90% of the AI infrastructure market, the sources say?
That's the strategic moat. It's not just faster chips. It's the entire vertically integrated ecosystem. Compare that to Intel.
Yeah. What happened with Intel? They were the kings of silicon for so long.
Well, they were perhaps slower to recognize the profound shift towards specialized processors for AI. They were focused on general-purpose CPUs, and they also arguably missed the boat somewhat on the rise of highly integrated system-on-chip, or SoC designs, which became crucial for mobile and then for specialized AI hardware. ARM-based architectures really ate into areas Intel might have otherwise dominated. It shows how missing that hardware pivot creates long-term strategic vulnerability.
So, for people thinking about corporate strategy, the lesson is clear. You can't separate the software strategy from the hardware strategy in AI.
Absolutely not. And it plays out in the economics, too. We should quickly touch on training versus inference.
Right. Training is building the model, inference is running it.
Essentially, yes.
Yeah.
Training is that incredibly computationally expensive upfront process. You need massive data sets and huge amounts of processing power, usually GPUs, working for days, weeks, even months. That's a huge capital expenditure.
Okay.
Inference is when you take that trained model and use it to make predictions on new data, like asking ChatGPT a question or identifying an object in an image. It still needs processing power, but often less than training, and it happens constantly, distributed everywhere. That's more of an ongoing operational expenditure.
And Nvidia positioned themselves to profit from both.
Exactly. Their GPUs accelerate both the massive training jobs and the widespread inference tasks. They captured value across the entire life cycle. That compute power they provided then enabled the next big software jump.
Which was the Transformers architecture from Google Brain in 2017.
That's right. Transformers allowed models to handle context and dependencies in data, especially language, much more effectively than previous architectures. And that breakthrough is the direct ancestor of models like GPT, and ultimately led to the explosion of interest with ChatGPT hitting the public in late 2022.
Incredible trajectory. Hardware enables deep learning. Deep learning proves scale works. Scale demands better hardware, which Nvidia provides with an ecosystem, which then enables even more sophisticated models like transformers.
A classic co-evolutionary spiral. But now let's shift gears a bit and bring in a more critical perspective, something really relevant for DBA or PhD level thinking. We need to circle back to John von Neumann, but this time his other major contribution, game theory.
Right. Theory of games and economic behavior with Morgenstern, 1944. How does that connect?
Well, think about the approach. Von Neumann's work, both in computing architecture and in game theory, involved a kind of radical simplification. To make problems mathematically tractable, especially problems involving human behavior, he had to reduce complexity. In game theory, this meant modeling human beings as rational actors, consistently maximizing their utility. He proposed this sort of axiomatized man.
Axiomatized man, meaning based on logical rules or axioms.
Precisely. To make the math work, assumptions were needed. Things like the transitivity of preference. You know, if I prefer apples to bananas and bananas to cherries, then I must prefer apples to cherries.
Which sounds logical, but
yeah,
human desires aren't always that neat, are they?
Not at all. Behavioral economics, psychology, heck, just reading a novel tells you humans are full of contradictions, changing preferences, self-deception. Von Neumann's model, while brilliant for certain kinds of analysis, sort of strips away that messy reality to achieve mathematical elegance.
Okay, I see the parallel. We solved the computational bottleneck of early AI, but maybe we've inherited a philosophical bottleneck from this reliance on logical reductionism.
That's the core question for critique. What are the strategic risks, the managerial blind spots, when we build this intelligence age on systems that fundamentally assume a simplified, logically consistent version of human behavior?
You deploy AI for, say, content moderation or financial trading, or even social credit scoring, based on these utility maximizing assumptions. What happens when they meet actual, irrational, unpredictable humans?
Well, you get misalignment, you get unintended consequences. Think about the Microsoft chatbot Tay back in 2016. It learned from humans, all right, but it rapidly became incredibly offensive because it optimized for engagement based on the input it got, without any deeper understanding of, well, human values or harm.
A stark example. The source mentioned von Neumann himself, worried about this gap, people not being able to keep pace with what they create.
He absolutely did. The fear isn't necessarily just rogue AI taking over, but perhaps more realistically, humans using these powerful, logically driven, but potentially brittle systems against each other, or systems optimizing for goals that diverge disastrously from human well-being because their underlying model of well-being is too simplistic.
Okay, let's try to synthesize some key takeaways from all this, especially for our listeners focused on strategy and innovation.
Right. First takeaway. Vertical integration in compute is major strategic leverage. Look at Nvidia. It's not just the chip, it's the whole CUDA ecosystem. Controlling that computational infrastructure or having a clear strategy for accessing it is non-negotiable in the AI era. Failure there is a massive business risk.
Got it. Hardware and the software stack around it are key strategic assets.
Second, economic scale is what defines capability in deep learning today. More compute and more data generally mean better models. For strategists, understanding the economics is vital, that huge upfront capital cost of training versus the ongoing distributed operational cost of inference. Managing that balance is critical.
Scale drives capability, and capability drives the need for scale. A feedback loop.
Exactly. And third, maybe the deepest point for scholars and thoughtful practitioners, mind the philosophical constraint. We have to constantly question the underlying assumptions built into these AI systems, especially those inherited from game theory and its simplified models of human rationality. We have to recognize that human psychology, culture, ethics, these aren't fully reducible to algorithms or utility functions. Designing systems that ignore this complexity, this non-rational element, actually increases systemic risk.
So the journey towards this intelligence age relies heavily on massive computation, energy, data. But the systems we're building, from chatbots to potentially autonomous weapon systems, are often based on the simplified, axiomatized view of us. Which leaves us with a final, maybe unsettling thought to reflect on. If we accept that von Neumann's powerful logic necessarily simplified the messy truth of human desires and contradictions, what else do we need? What kinds of new thinking, maybe new kinds of research collaborations, bringing in humanities, social sciences, ethics, are essential to build AI that can actually handle and hopefully enhance the full, complex reality of being humans? That feels like the next frontier.
Thanks for tuning into the Lion's Share podcast. If you enjoyed today's discussion, share it with a friend and join us next time for more ideas worth talking about. We'll see you next time.